Hey everyone. So far we have gone ahead and talked over how objects can move in one direction. In this case, I've got a ball. It can go up and down, or it can go down and then up. And that right there, that's one-dimensional motion. So we figured out how to do one-dimensional motion. We've got some equations that help us do one-dimensional motion. But now we need to figure out what happens if an object chooses to move in two dimensions at the same time. So we could go up and down, and we can go left and right with the way that we currently do things. But what happens if a ball goes up and down and left, right, or forwards and backwards at the same time? So for instance, if I throw a ball over there, I'll get that later. So that's what we're referring to as projectile motion or two-dimensional motion. So we're going to be looking at what happens if I've got an object that wants to move in two dimensions at the same time. How do I deal with a circumstance like that? And how can we break this down to make this as easy as possible? So let's start with what we already know. We know that velocity tells us how position changes relative to time. And we know that acceleration tells us how velocity is changing relative to time. And then we were given three equations that we could use to figure out other variables if we had some information to work with. So we could figure out the final position of an object or its velocity and things like that. And those were all things that we covered in Unit 1. And the nice thing is we're going to take all of these equations and they still apply in two-dimensional motion, because the big difference here is that we're going to be dealing in either the x direction or the y direction. Now let me go ahead and show you how that actually works. So let's say that we have a ball being launched out of a cannon. Okay, so I've got a nice flat surface. I'm going to draw a very rudimentary cannon here. Okay, and we've got a ball that is going to get launched out of it. Okay, so this would be a classic projectile motion problem. And in fact, most of the examples that I'm going to use are involving something being launched out of a cannon, to be fair. So what's happening is after this ball leaves, the ball is going to travel up and it's going to travel to the right, and it's going to do that at the same time. And so if I go ahead and kind of track the projectile arc of this ball, it's going to look something like that, right? Now I want you to think of this in terms of data points. So let's say if I was to measure or identify the position of the ball every second, I might do something like this. So here's at time 0, here's 1, 2, 3, 4, and so on. Now if I do this, I can go ahead and I can look at how position is changing over time. So I'm looking at velocity here. And I can do this simultaneously in both directions. So from 0 to 1, I can identify I've definitely had a change in the y direction. And I can also identify there's been a change in the x direction. And because I can kind of break this apart as a change in a y direction and a change in the x direction, I can work it as one or the other. So I can use this to help me kind of understand that it's moving both in the y direction at one time and in the x direction at the same time. So you can see from that example that we have the ability to deal with two dimensions at the same time. We just have to kind of separate the two of them and work them separately. But the question is, what keeps them together? And that right there is a variable that is going to be constant regardless of what direction you are going in. And that is time. See, at the same time that this ball could be going up and down or left and right, time is holding both of those equations together. So if I'm moving at an angle like this, I can measure the change in my y position versus time, and I can measure my change in x position versus time. And if I use both of those together, I can use time to go ahead and kind of bind my two dimensions together in the same way. So that helps us get kind of a basic understanding as far as how we can do two dimensions at the same time. We just have to make sure that we are literally using the same time. Now that's all well and good, but where do I get my starting numbers from if I have an object that launches at an angle, so it's moving in two dimensions simultaneously? So let's go to another cannon example. In this case, I'm going to have, once again, I'll have my nice cannon. It's It's going to shoot a tennis ball. But this time, we're going to go a little bit more detailed with it, because I'm going to know this is a 40-degree angle, roughly. And my tennis ball that is being launched, I know this has an initial velocity as soon as it leaves the cannon of, let's give it 60 meters per second. Now this is, once again, kind of the setup that you'll be working with when you're dealing with two-dimensional motion. So I've got an initial velocity here, and I've got an angle that I'm working with. And so the first thing I'm going to do is I'm going to realize that what we really have here is a right triangle where I've got 60 meters per second on the hypotenuse. That describes how it's moving in both directions at the same time. Now I can go ahead and break that into its x component and its y component, because I have an angle right here that is 40 degrees. And so at this point, if you've had a little bit of slightly more advanced math, or you've taken some trigonometry, you should immediately recognize we're going to have to use three different functions that can help us kind of break this thing down. And so if you're familiar with them, you'll recognize immediately sine, cosine, and tangent. And we're going to use sine, cosine, and tangent to break down this formula into its x and y position. Now, working with sine, cosine, and tangent typically involves a little kind of word game that people came up with that looks a little something like this. This is SOHCAHTOA, and we're going to use SOHCAHTOA quite a bit. What this means is that if I'm ever using sine, I'm going to look at my opposite over my hypotenuse. If I'm ever using cosine, I'm going to use the adjacent over the hypotenuse. And if I'm ever using tangent, that is going to be opposite over adjacent. So what sine, cosine, and tangent do is they are ratios for the length of legs based on the angle of something. So let's say I have a hypotenuse of 60 meters per second, and I have an angle of 40, and I'm going to go ahead and solve for my x velocity first. So here's my angle. This is what is called the adjacent leg of the triangle. So this is going to be A, and 60 is my hypotenuse, so there's going to be H. So I have A and H. I'm going to use cosine for this. And so what this means is that cosine of my angle, 40 degrees, is equal to adjacent over hypotenuse. A divided by H, or in this case, it's going to be the leg X that I'm looking for divided by 60. So, at no point do I expect you to memorize the cosines, sines, or tangents of anything. So I'm going to go ahead and take my trusty calculator here, type in cosine of 40, and then I see if I want to get x on its own, I'm going to multiply both sides of this thing times 60. So I'll multiply it by 60. These will cancel out. I'll multiply this by 60. And I'll find out that the x value, or the x leg of this triangle, is actually going to equal 45.96, and that is in meters per second. So if the ball is traveling at an angle at 60 meters per second, its x position is changing at 45.96 meters per second. And I can go ahead and I can repeat this process to find my y angle. So in this case, if here's my angle, this is going to be the opposite side of things. So I have an opposite and I have hypotenuse. I'm going to use sine in this case. So, because I need to get myself a little bit more working room here, I'm going to have the sine of 40 degrees is equal to opposite over hypotenuse. So opposite over hypotenuse, also known as my y position, divided by 60. And again, I'm going to turn to my trusty calculator. I'll do the sine of 40 degrees, and I'm going to multiply both sides by 60 to make sure that I get my variable all on its own. These will cancel. And so I'll type in times 60, and I can see that my y position is changing by 38.57, roughly, meters per second. So now that I've got my information, let's just kind of recap what I've learned from this little triangle right here now that we're done. I know that my initial speed is 60 meters per second, but that is traveling both the x and y directions simultaneously. And in order for me to work this problem, I need to figure out how it's moving in each direction individually. So I went ahead and used sine, cosine, and tangent to solve this problem. I found out that in the x direction, my position is changing by 45.96 meters per second. And in the y direction, I'm moving at 38.57 meters per second. So now I have separate numbers for how this thing is moving. And since this is an initial velocity in general, these are going to be initial velocities as well, just in this case, in the y direction or the x direction. So while that gets us our basic set of starting numbers, we do realize that as the object moves through the air, that something is causing it to change. And for most of us, it's obvious, but let's think about this for a second. If there was absolutely nothing acting on the ball after it leaves the ground at an angle, it would just keep going on and on and on at that angle forever. But it doesn't do that. And so we have to have a reason why. And the answer that should immediately be popping into your head right now is gravity. Gravity is the thing that is changing the ball's movement. It is an acceleration. It is changing the velocity of the ball. But gravity only changes the velocity of the ball in one dimension. Gravity isn't affecting it in the x direction. Gravity pulls down. So gravity is only working in the y direction, and that is an important thing to keep in mind. So there is an acceleration that is acting on the ball that is changing its velocity, but it only changes it in the y direction. And since most of our problems we can ignore air resistance, nothing is going to happen to the velocity of the ball as it travels in the x direction. So that's all well and good, and it might help you understand a little bit about projectile motion. But I know that most of you really need to see an example problem worked out for this. So let's go ahead and take a look at a classic example of an angled launch on a flat surface. So let's go ahead and finish the problem that we started when we talked about how to break things down with sine, cosine, and tangent. So my triangle looked something like this after I broke down the initial velocity of 60 meters per second into its x and its y components. So let's go ahead and finish this problem, and I'm going to try to figure out the total change in position, or the total delta x, of the projectile. That is going to be my goal for this one. We're going to find out the range of the cannon, if I could spell. There we go. So the first thing that I want to do is I want to figure out how long the object is in the air. And that means I need to figure out t. I need to figure out the number of seconds that the object is in the air. So let's go ahead and kind of take a look at another example that I gave earlier. This one with the numbered positions. I'm moving over in the x direction by the same amount every second. But the only thing that's changing is the ball's y position, so gravity. So in order for me to figure out how long my object is going to be in the air, I need to figure out how long does it take for the ball to go up and then back down to its original position. Now in order to do that, I need to make a couple of opening assumptions. So first of all, this ball is being launched on a perfectly flat surface, which means by the time that the ball goes up and then comes back down, it will have a total change in the y position of 0. It is going to go up and then it's going to come back down, and it's going to end at basically the same point that it started at. So that's a total change in the y position of 0 meters. The other thing I know is that the only acceleration acting on the ball is gravity, and that pulls down on the ball at 10 meters per second squared. So I've got a couple of little pieces of information that I have to work with. I've got a change in position, I have my acceleration, and of course from up here at my triangle, I have my initial velocities. So in the y direction, my initial velocity was 38.57 meters per second. So I have my three variables, and I want to solve for time. So time is the thing that I don't know. So let's go ahead and solve for time then. If I have a change in position, an acceleration, and an initial velocity, looking back at my equations, I'm going to find out that the best equation to use here is that delta y is equal to vi times t plus 1/2 at squared. I can go ahead and start plugging some stuff in. I know that delta y is going to be equal to 0. Velocity initial was 38.57 times t plus 1/2 10 t squared. All right. Now we can go ahead and kind of distribute this if we really wanted to. So I've got 38.5 t. This is 1/2 of 10 is 5, so this is plus 5t squared, and this thing is equal to 0. So at this point, let's go ahead and figure some things out. Actually, I just realized I did make a critical error here, so please don't make the same error that your teacher just made. Gravity is in the wrong direction, the way that I've put it. I've already defined upwards as being a positive number, so if gravity is going to be pulling downwards, gravity should be negative. So be careful with that one. I just made that mistake. So this should really be a negative 5t squared, and that's going to be important. Because what we're going to do is I can subtract 5t squared, actually I'm going to add 5t squared to both sides of my equation, and I'm going to get 5t squared is equal to 38.5t. And what you should see is that I can go ahead and divide t on both sides. That'll get rid of this, and it will strike this. So 5t will be equal to 38.5. So therefore t is going to be equal to, if I divide that by 5, 38.5 divided by 5. This ball is going to be in the air for 7.7 seconds. So here is the total amount of time that my ball is going to hang out in the air. And that is actually the hardest part of what we're doing, because now that we know that the ball is in the air for 7.7 seconds, we can now take this and our velocity, and we can figure out how far it went. So let's finish this up and see if we can find the total range of the cannonball. So if I know that my total time is 7.7 seconds, I'm going to go ahead and get a little bit of extra scrap paper here. All right. And I know that the initial velocity of the ball in the x direction is 45.96. So I have a velocity in the x direction of 45.96. I can ignore air resistance, so it's never going to slow down, so it's just a velocity. And I know I have a time of 7.7 seconds. I can go ahead and work with my definition for velocity, which tells me that v is equal to my total change in position over time. Now I can go ahead and rearrange this because I'm trying to figure out how far it went. I'm going to go ahead and multiply both sides by t. These will cancel out. And so v times t is equal to change in position. How fast I'm going times how long I'm in that speed is going to tell me how far it went. So now I can go ahead and plug some stuff in. 45.96 is my speed. 7.7 is my time. And so my total change in position is going to equal a fairly large number. Here we go. 353, basically 0.9. And that's just meters. There we go. So this is the total distance that the ball will travel given the information that I had right here. So there's our process for finding two-dimensional motion. I know it's a bit long and drawn out and it does a lot of math, which means some people are going to love this process and some people are reasonably going to hate it. But either way, you need to know how to deal with two dimensions at the same time. So to kind of recap, the first thing we do is we go ahead and break our launch angle into components, both x components and y components. Then we use our y component to figure out how long the ball is in the air. And then we use our speed in the x direction, and we take our time from y to figure out how far it travels before it hits the ground. So hopefully that was helpful. I look forward to seeing all of you in class, and good luck with this week's assignment.